Fantastic. Let's get after it. 4.6 inverse function. So what is an inverse function? An inverse function is a function that undoes what another function did. So let's say I'm looking at a function, something pretty simple like adding 3. Then the inverse function subtracts 3. If I'm talking about a function of dividing by 2, then the inverse function would be multiplying by 2. And of course, we can combine different operations, different numbers to make these types of functions. Reminder, a relation is only a function when each input has only one output. So the inputs or the independent variables or the x's cannot repeat. So you have a table example right there where this is my original function. And this symbol right here, f to the power of -1, that is the notation for inverse. So this notation right here means inverse function. It's actually not raising anything to a power. It's just a notation that means inverse. So what happens when I'm looking at a relation and its inverse, or a function and its inverse, is the x's and the y's switch positions. So what was once the input becomes the output, and what was once the output becomes the input. I have them written in table form here, but we could also look at them in list form. So this coordinate right here, 3, 10, when I look at the inverse, becomes 10, 3. The coordinate 4, 13 becomes the coordinate 13, 4. And so on, right? 5, 16 becomes the coordinate 16, 5, and 6, 19 becomes 19, 6. So everything in the x just gets exchanged with y. An additional question here says, is the inverse a function? So I can determine something's a function to make sure that none of my x values repeat. So, do I have any same x values? No. So is the inverse a function? Yes. And I'm just going to write in parentheses here how I know. So here's just another example for us to do on our own. Write the table for the inverse relation, and then is the inverse a function? This table is just written horizontally to give you a different perspective. For the original function, I have x values of -2, -1, 0, 1, and 2. and y values of 4, 1, 0, 1, 4. Okay, so I'm just going to swap the lists. This is the coordinate negative 2, 4. So when I'm looking at the inverse, the new coordinate is going to be 4, negative 2. Now, again, I have it written as a table. You may also see this written as a list of points. It could be written like this. And you could just peek at this, or you could write it down, whatever works for you. Oh, running out of room. All right, I can have this as a list of points. And then I could just as easily write the inverse in this manner. Same meaning, just a different way to see it. So for my original function, my point is negative 1, 1. And the x and the y swap. And I get 1, negative 1. Zero, 0. Those positions swap. It's actually the same point, and that's okay. One, 1 swaps. And then 2, 4 becomes 4, 2. So you could see it written as a table, vertical table, horizontal table. There it is as a list. All the different modes. Cool. So here's the new table. Then it says, is the inverse a function? Well, the inverse is a function if the x values do not repeat. So I check out the x values, and I have 4, 1, 0, 1, 4. Is that a function? No, it is not. And it's not a function because the x values repeat in the inverse relation. Relation is just a very general term, right? It doesn't have to follow any rules. Yeah. See how there's 2 4s? It repeats. Yeah, there's 2 1s. Right? There's duplicates. They have to be unique in order to be a function. Only occur one time. All right, so that's looking at tables or coordinates. And now we're going to look at functions in an equation form. So to find the inverse of an equation, I'm always going to write it as y equals, and then I'm going to literally exchange x and y, solve for y, and then rewrite with my inverse notation. All right. So here's my steps. Step 1, instead of f of x, I'm going to write it as y. So I'm going to replace f of x with y. Then I'm going to swap x and y. So instead of y, I'm going to write an x. Instead of x, I'm going to write a y. Then I solve for y, however many steps that's going to take. So to solve for y, the first thing I'll have to do is subtract 1 from both sides. And then to get y by itself, finally I have to divide by 5. When I divide by 5, I have to do it by the entire side of the equation. Then the last step, instead of y, I'm going to replace this with f inverse of x, because now I found the inverse, and I want it to not look like an original function. That is the inverse equation. So I substitute y in for f of x. I just made a change. They're equal. Not a big deal. And then my strategy is I'm going to transpose x and y. I'm going to switch them. So I just wrote x where y was and y where x was, and then solve for y. Here's my original function. This notation means it's my inverse. So I always want to use that notation. So replace this final y with f inverse of x, and I get x minus 1 divided by 5. The original function was times 5 plus 1. And so the inverse function is subtracting 1 and then dividing by 5. Final question asks, is the inverse a function? And yes, it is. And we're going to look at a graph here as one of our ways to determine if it's a function. So I'm going to scroll down. I'll come back for example B. But I have this graph on here for us. And some information. Graphically, the inverse function is a reflection of the graph over the line y equals x. So here's the idea. We'll give you a chance to copy that down before I talk about it. Okay, cool. So when looking at this on a board or on a projector screen, it's a little bit tougher. On your paper, it might be actually a little easier. So graph the function 5x plus 1. That's just a line, slope of 5, y-intercept of 1. So I've got a y-intercept of 1, and then up 5 over 1, and I draw this line. Cool. The inverse function, all right, if I were to take this and rewrite this, I would have if I wrote this as 2 fractions instead of 1 fraction, I would get this. It's equivalent, but it's more of the way that we're used to graphing things. Right? So I have a slope and a y-intercept. That's okay. I just graphed it in decimal, so you don't have to do it by hand. But that's why I've got an intercept here at negative 1/5. And then up 1 over 5 is a very shallow slope. So imagine this, and you can do this with your actual paper. I can't do it with the projector board or the screen, but that green line is what it's reflected about. So if I were to take my paper and I were to fold it on that green line, the red function and the blue function would line up perfectly. When that happens, they are inverses. All right. We'll talk about restricting later, but graphically, that's what it looks like when I have 2 inverses. They would be on top of each other when I fold the paper from top right corner to bottom left corner, which is the line y equals x. I'm going to scroll back up to do example B, and then we'll come back to graphing. Example B, f of x is equal to parentheses x plus 4 and parentheses all cubed. So my steps, I'm going to replace f of x with y. It's just easier to manipulate. It's easier to move around without losing parts. Then they exchange x and y. So just rewrite it so that the x is in the y position and the y is in the x position. And then we solve for y. When solving for y, it's important to use our order of operations. I need to start on the outside and work my way in because I've got some parentheses. So the first thing I'm going to do is I'm going to take the cubed root of both sides. The cubed root of y plus 4 cubed is just y plus 4. Raising something to the power of 3 and taking the third root are inverse operations. And then just subtract 4. Now the minus 4 does not go underneath the radical. It's outside of it. And the final step, I'm just going to rewrite this instead of y. Y is confusing because I can't tell with this notation which one's the original, which one's the inverse. So I'm just going to rewrite it with my inverse notation. And I have the cubed root of x all minus 4. We're going to look at graphs before we talk about if it's a function or not. All right, I'm going to leave this page and I'm going to go graph both of these functions in Desmos so we can look at what they look like. We haven't done a lot of graphing cubed roots by hand. We did a little bit of it. So the first function was f of x is equal to x plus 4 to the power of 3. So a raising 7 to the third power kind of gives me this wavy shape. And then the plus 4 inside shifts this from the origin to left 4. That's my original function. And I'm going to use g of x for my inverse function. I need the cubed root. I don't know. Yes. Haha. Awesome. Cubed root of x. And then minus 4 outside. So I have to cursor over. And then I have these graphs. Sometimes it's helpful to look at the actual line y equals x. And if I zoom out a lot, hopefully you can see that one is a reflection of the other in your mind, which is really difficult to do. If you could imagine folding this picture on the dashed green line, hopefully you can tell that it is a reflection. Oh, what am I doing? Zoom in. Okay. So we are going to jot that down. I'll give you a moment if you'd like to copy down from the screen, and then I'll copy down on the screen for us. It doesn't need to be super precise. Most of these ones that you're going to be looking at are going to be multiple choice, so just kind of understanding the general shape and being able to tell when it's a function and when it's not. And when it's an inverse and when it's not. This window is a bit more zoomed out than mine, so this is a clearer picture on Desmos than it is on my notebook. When I graphed it on my notebook, it looks like this. And that's just because my window is a little smaller. All right, so those are inverses. They would kind of land on top of each other if I were to fold it across that dashed line. And then the second question in example 2 says, is the inverse a function? All right, so let's talk about how we can tell if it's a function given a graph. If you remember back to, I think in math 1, you talk about determining if something is a function by looking at the vertical line test. So the vertical line test says that I can draw an arbitrary vertical line and not cross a relation more than one time. So if I were to take any vertical line, doesn't matter, I have to be able to draw it anywhere. Those are not perfectly vertical, but work with me here. Am I ever going to cross that blue graph more than once? No. That means that yes, it's a function. So, yes, it's a function. And I'm going to put in parentheses, it passes the vertical line test. And sometimes the best way to tell, I could sit there and I could plug in values for that. I could try to memorize some rules, but sometimes the best way to tell is just to look at a quick graph. We've talked about a linear example, a cubic example. They're both functions. Let's talk about something that's not a function. So we have functions, which means that I have all unique x's. I also have something called a one-to-one function, where every range value has exactly one domain value and vice versa. A one-to-one function means that there's no repeating terms in the domain and no repeating terms in the range. No repeating x values and no repeating y values. A function passes the vertical line test, but a one-to-one function passes the horizontal and the vertical line test. The two examples that we looked at above, A and B, the linear and the cubic, are both one-to-one functions. In the homework, they use this terminology, so I just wanted you to be aware of it. And then example C, same directions, find the inverse equation and is it a function? For problem C here, f of x is equal to x squared minus 3. When I have even exponents, things change a little bit when I look at inverses. Okay. Okay, so I will replace f of x with y. I'm going to exchange x and y. And then solve for y. So first thing to solve for y, I got to add 3 to both sides. And to get y by itself, I take the square root of both sides. When I take the square root of both sides, I always get positive and negative, or plus and minus. And finally, I'm going to rewrite this with my inverse notation. Graphing a parabola. Y equals x squared is just my parent function that usually goes through the origin. And then for this one, I just need to shift it down 3. All right, so vertical shift down 3. And then my a value is just 1, so I'm going to go over 1, over 1, up 3, over 1, up 5, but it doesn't quite fit. A parabola, a quadratic, is a function. It passes the vertical line test. I could draw any vertical line anywhere I want, and it's only going to cross this purple graph one time. When I graph the square root function, which we've had some practice with, square root function is a shift left 3. This is the positive square root function. And then this is the negative part. So here's my inverse. The second part of the question says, is the inverse a function? So this is an example of it not being a function. It's written on there twice, but that blue graph would not pass the vertical line test. If I were to draw an arbitrary line, right, then that would cross the green graph or the blue graph more than one time, right? That means that it's not a function. So then we get into the conversation with how can I restrict quadratics to make them functions? And that's kind of we're going to dive deeper into that another time. And today we're just focusing on recognizing when it's a function and when it's not. All right. That wraps up these notes for today's purposes.